Welcome to Introduction to Building Codes. Today's presentation is the Bangladesh National Building Code 2020. We refer to that as the BNBC-2020. Part 8 Building Services, Chapter 2 Air Conditioning, Heating, and Ventilation, Part 1 presentation. The description of this presentation is designed to familiarize and assist code officials, inspectors, engineers, designers in not only locating the code sections, but describing and applying the applicable code requirements for air conditioning, heating, and ventilation systems. The overview. Internationally, code officials recognize the need for a modern, up-to-date mechanical code that addresses the design and installation of mechanical system through requirements, emphasizing performance. This presentation will cover key topics of the following areas. We will cover scope, application, and terminology. Terminology is so important. We need to understand certain language for mechanical systems. We will go over that systematically and accordingly. Second part is general provisions and planning, and then we'll finish up with the air conditioning system design with the focus on mechanical ventilation systems and natural ventilation. The seminar goal. The goal of this training is for you to learn and apply key code requirements contained in Chapter 2, Air Conditioning, Heating, and Ventilation, to enhance your performance while inspecting these systems. We will also give you examples and applications based upon design criteria and examples as well. This training will also provide participants with specific examples related not only to design, but installation and inspection of air conditioning, heating, and ventilation systems to further enhance your knowledge. The objectives of this presentation will allow you to be better able to locate general topics in Chapter 2 regarding air conditioning, heating, and ventilation. Locate applicable codes and standards for specific situations. Apply code requirements to real-world situations. And explain the intent behind a given code requirement. We need to understand that the intent behind a given code requirement needs to be explained. It needs to be applied based upon applications. We'll go over that systematically. And finally, using good judgment to identify certain systems and related components, either as being compliant or non-compliant. And this is based on the requirements set forth in Chapter 2. Specifically, we will focus on ventilation systems towards the end of the seminar, and we'll have examples showing you the proper application of these requirements. Chapter 2, Section 2.1, General. The purpose of this chapter is to provide minimum standards, not only for regulating and controlling the design, but also the construction, installation, quality of materials, location, operation, performance, as well as maintenance and the use of air conditioning, heating, and ventilation systems to ensure acceptable conditions of air inside the building required for human health, safety, and welfare with energy conservation. An air conditioning, heating, and ventilation code cannot be effective without adequate provisions for its administration and enforcement. The authority or the official has the responsibility for establishing that the homes in which the citizens of the community reside and the building in which they work are designed and constructed to be reasonably free from hazards associated with the presence and use of mechanical equipment, appliances, and systems. We have this code as it states in the language that was initially introduced to provide human health, safety, and welfare with energy conservation. The code is designed with requirements, design criteria that engineers must use to properly design these systems, inspectors to inspect these systems, and this way the end result is a safe and healthy environment for everybody within homes and buildings. The official or the authority is charged with the administration and the enforcement of mechanical regulations and also has great responsibility. And with this responsibility drives authority. We need to make sure that not only the design, but the installation complies with the requirements of this code. Quality of materials are so important. The air conditioning, heating, and ventilation code intends to establish a minimum acceptable level of safety. We can exceed what the requirements are in this code, but we can never go below the minimum acceptable thresholds in this code. So let's take a closer look at specific sections related to scope, application, and terminology requirements for air conditioning, heating, and ventilation systems. Section 2.2, Scope. Specifically in Section 2.2.1, it indicates the provisions of this code shall apply to not only erection, but also installation, alteration, any repairs, maybe relocation of equipment, appliances, replacements are covered, as well as additions, maybe additions to air distribution systems, hydronic piping systems, things of that nature. Also use and maintenance of any air conditioning, heating, and ventilation systems. This section gives us the driving language as code users to understand our scope to get into this particular code. This section describes the types of mechanical systems covered by the code. The code is applicable from the initial design of mechanical systems through installation and construction, and finally into the maintenance of operating systems. Our systems must be maintained. They must be cleaned regularly. They must comply with the manufacturer's installation instructions and maintenance as well for proper operation through the life of these systems. The scope of the code is primarily focused on heating, ventilating, and air conditioning systems, HVAC systems. Those items specifically addressed in the code and those building service items that make a building comfortable, functional, and safe. In section 2.2.3, this key section gives us the requirement where in any specific case, different sections of this code specify different materials, methods of construction, or other requirements. We need to look at the most restrictive one as that shall govern. Where there is a conflict between a general requirement and a specific requirement, the specific requirement shall be applicable. The first part of this section essentially describes where there could be dual coverage and states that the most restrictive prevails. We will look periodically at a general requirement giving maybe a general layout, maybe a general area of installation. Whereas when you get deeper into the code, it may address a requirement more specifically based upon your application, which will have to be evaluated and looked at to be the most restrictive. The code official must carefully evaluate each application regarding materials, methods of construction, or other requirements and make decisions that provide the greatest safety. And as mentioned previously, this is where authority comes in. We need properly trained people to administer this code, properly trained and technical people to enforce the code as well. The second part of this section describes if conflicting coverage is encountered, then the specific requirement is to be applicable. Conflicts within the code do not often occur, but if they do, this section applies. Chapter 2, Section 2.3, Application. It shall be unlawful to install, extend, alter, repair, or maintain air conditioning, heating, and ventilation systems in or adjacent to buildings, except in compliance with this code. This section, ladies and gentlemen, is telling the code user that we need to comply with this code, not only for design and installation, also extending systems. In the graphic below, we see that we have a hydronic piping system that has been recently extended from one part of the system to a new part for a building addition. It not only lends itself to installations, extensions, but also alteration, repairs, and maintenance as well. So the application covers everything with respect to the air conditioning, heating, and ventilation systems. This is the initial language and requirement that we need to get into in Section 2.3. Section 2.3.1 is now specific to existing installations. Air conditioning, heating, and ventilation systems in existence at the time of adoption of this code may have their use, maintenance, or repair continued if the use, maintenance, or repair is in accordance with original design and location, and no hazard to life, health, or property has been created by such system. What this section is telling us specifically is the existing mechanical system is generally considered to be allowed to continue in accordance with the original design if the system meets a minimum level of safety. We need to be concerned with the proper maintenance of these systems to keep them functioning as originally designed. The air conditioning, heating, and ventilation systems, of course, must continue to be properly maintained, properly repaired, and function, of course, as they were originally designed. Maintenance is so necessary to keep the mechanical systems and equipment safe and in proper operating condition. Additions, alterations, or repairs. This is getting, again, more specific as it relates to additions of systems, alterations of systems, or repairs of systems that may be made to any air conditioning, heating, or ventilation system without requiring the existing system to comply with all the requirements of this code, provided the addition, alteration, or repair conforms to the requirements of a new system. Additions, alterations, or repairs shall not make an existing system unsafe, create unhealthy or overloaded conditions. Now, this last language is the driving language of this section. As code users, we must understand that the existing systems have the right to exist, provided they have been maintained as originally designed and function accordingly, as we saw in the last slide. However, if we decide to provide any alteration or an addition to an existing system, it involves some extent of new work, then the new work is subject to the requirements of this code. If we decided to analyze an existing air distribution system for air conditioning based upon a new building addition, and the engineer found that the existing system has enough capacity to serve the addition, then the new work would have to be compliant with the new code requirements. So we take it from the existing system where we tap off of or extend from, and all of the work from that point to the new addition is required to comply with the current code. Additions or alterations can place additional loads or different demands on an existing system, and those loads or demands could necessitate changing all or part of the system. So it's very important that we analyze the existing systems due to, again, these additional loads or different demands. A duct addition example is shown here. The language in the code section that we just discussed, additions, alterations, or repairs, shall not make an existing system become unsafe or create any unhealthy or overloaded conditions. The picture below shows a new air distribution supply duct added to an existing system. Prior to adding the ductwork, the existing air distribution system was analyzed to verify the added demand on the system, and was found that there was enough capacity to supply a new branch to a new building addition. This installation from the attachment of the existing system must comply with the new code requirements. Changes in building occupancy. Air conditioning, heating, and ventilation systems, which are part of any building or structure undergoing a change in use or occupancy, as defined in the building code, shall comply with all requirements of this code, which may be applicable to the new use or occupancy. When a building or any part of a building undergoes a change of occupancy, not only the building but the mechanical system must be evaluated to determine what effect the change of occupancy has on it. And depending on the nature of the previous occupancy, changing a building's occupancy classification could result in a change to the mechanical system. A change in occupancy could require changes to an existing mechanical system to accommodate the needs and requirements for the new occupancy. We may be into exhaust systems. We may be into increasing the ventilation, bringing in more outdoor air to dilute contaminants in certain areas and zones of the building, whereas the previous occupancy did not have such a high demand. And again, it's all dependent upon the new use or occupancy that the building or space is being changed to that must be analyzed. Consider an office building that will be converted to a restaurant. The mechanical systems must be altered as necessary to comply with what the code prescribes for such assembly occupancies. This is clearly a change in occupancy, or in other words, the existing office building will function much differently as a restaurant. The restaurant is more densely populated in the dining room, whereas if you have an office building, we do not have such a dense population occurring in office buildings. Additionally, with a restaurant, we may have a commercial kitchen installed that we need exhaust systems, makeup air systems, and heating, cooling, and ventilation systems installed for that function within the new restaurant. Outdoor air may be required for the dining areas. Hoods and makeup air will be required over the cooking equipment. And exhaust ducts may require shafts or enclosures that must be compliant with the building code requirements. These are just a few of the mechanical system issues in such a change in occupancy. The change of occupancy indicated in the photos below involved an existing office building that was converted to a restaurant. This is considered a change of occupancy. The office building was converted to a restaurant that includes a dining room and a brand new commercial kitchen. The new commercial kitchen required new air conditioning, new exhaust systems, a makeup air system, and ventilation systems to be installed. And as you can see in the picture on the left-hand side, we have the exhaust equipment and appliances coming through the roof of the building. Additionally, the seating area of the restaurant required the existing air conditioning system to provide more ventilation, regarding more occupants in that area. This is a mechanical ventilation system that brings in outside air. It was analyzed and modified to introduce more outside air in liters per second and was calculated for the occupant density given this new change of occupancy. And further along, we will have an example coming up of a ventilation requirement for mechanical ventilation, and we will go through a step-by-step procedure and show you how to calculate minimum ventilation rates for outside air to be brought in mechanically into our buildings. Maintenance. All air conditioning, heating, and ventilation system, materials, and appurtenances, both existing and new, and all parts thereof shall be maintained in proper operating condition, in accordance with the original design and in safe, hazard-free condition. Additionally, we need to look at this last couple of sentences. All devices or safeguards which are required by this code shall be maintained in accordance and conformance with this code. The owner or the owner's designated agent shall be responsible for maintenance of the systems and equipment. Maintenance is necessary to keep the mechanical systems and equipment safe and in proper operating condition. We typically have safety devices, controls that need to be maintained in order to continue providing the protection that they afford. Additionally, all safeguards required by the previous or present codes must be maintained for the life of the equipment or systems served by those safeguards. Lastly, the maintenance comes in, and it was indicated the maintenance of mechanical systems as prescribed in this section is the responsibility of the property owner. The owner may authorize another party to be responsible for the property, in which case that party is responsible for the maintenance of the mechanical systems involved. Section 2.3.2 contains requirements for alternative materials and methods of construction. The provisions of this code are not intended to prevent any use of any material or method of construction not specifically prescribed by this code, provided any such alternative material and or method of construction has been approved and the use authorized by the authority. The fact that the material or a material, a product, or method of construction is not addressed in the code is not an indication that such material, product, or method is intended to be prohibited. The authority is responsible for determining if a requested alternative provides the equivalent level of protection to public property, health, safety, and welfare as required by code. Now, an alternative material may be an application-related material that fits the engineered design and can be approved by the authority. The authority shall require that sufficient evidence, however, or proof be submitted to substantiate any claims made regarding the use of alternatives. As stated in this particular requirement, the alternative material or method of construction may be approved where, in fact, the authority finds that the proposed design is satisfactory and complies with the intent of the provisions of this code, and that the material, method, or work offered is for the purpose intended, not less than the equivalent of that prescribed by this code in quality, strength, effectiveness, fire resistance, durability, and safety. So as you can see here, given that we do have the alternative materials and methods of construction section, the main part of this requirement is that the quality of materials, perhaps, the strength of materials, the effectiveness, even fire resistance rating, along with durability and safety, is a key requirement that must be analyzed and proven to the authority. Once the authority has that data, then the authority can approve alternative materials and methods of construction. An example is the ICC Evaluation Service Report. Testing methods specified in this code or by other recognized test standards, along with the testing performed by approved agencies, can be submitted to the authority. This is a mechanism that can be submitted to the authority for approval. These research reports from approved sources may be submitted when an alternative material or method is proposed for construction. The ICC Evaluation Service is just one example of an agency that provides research reports for alternative materials and methods. Modifications. Now, modifications are not prohibited by the code. The authority, within the limitations set forth in Part 2, of course, may allow modifications for individual cases. The modifications, however, must be in conformity with the intent and purpose of the code, and that such modification shall not lessen health, life, and fire safety requirements. Now, this may be a modification to maybe a piping method being installed, maybe a duct method, or even a material, things of that nature, that must be modified given an application. Again, the authority should be provided with the analysis and intent of the modification in order to make a good decision, and if the modification fits the intent of the code. So the code official or authority may amend or make exceptions to the code as needed, where strict compliance is impractical. This section is not intended, however, to permit setting aside or ignoring a code provision. Rather, it's intended to provide acceptance of equivalent protection. As in construction, there are changes, there are modifications, there are amendments all the time, and we have to work through the process as engineers, installers, inspectors, and authorities. Section 2.4, Terminology. Terminology is key, ladies and gentlemen. We need to specifically understand certain words, or maybe even a single word within a code section to fully understand the intent of the code. So it's very important that we understand the language of air conditioning, heating, and ventilation. This section provides an alphabetical list of the terms used in and applicable in this chapter of the code. In case of any conflict or contradiction between the definition given in this section and that in Part 1, the meaning provided in this section shall govern for interpretation of the provisions of this chapter. Now, a code provision could be misinterpreted if the definition of a term as used in the context of the code is not understood. This reinforces why we need to understand the terminology for air conditioning, heating, and ventilation systems. The following slides will provide key definitions that will assist the code user to properly understand certain terminology related to this chapter. Codes, by their very nature, are in fact technical documents. As such, literally every word, term, and punctuation mark can add to or change the meaning of the intended result. This chapter contains several terms that are important to understand the provisions of this code. Definitions are found both in this chapter and throughout the code. Let's look at some key terminology relating the air conditioning, heating, and ventilation systems. Air change. Air change, by definition, is introducing new, cleansed, or recirculated air to conditioned space, measured by the number of complete air changes per unit time. The following example provides an illustration and calculation of an airflow rate entering and leaving a space. The calculation provides a number of air changes per hour, given the airflow rate and volume of space. As seen, we have a volume of space that essentially measures 1,000 cubic meters. We have an airflow rate entering at 100 liters per second and an airflow rate leaving at 100 liters per second. The air leaving would be, in fact, the exhausted air, while the entering air is new air, completely cleansed or recirculated to the conditioned space. The air change per hour expression, or the equation below, is as follows. The unit time we will use here is 1 hour. Air changes per hour equals the quantity 60 times the airflow rate in liters per second divided by the space volume. So in this example, we simply take 60 times 100 liters per second divided by 1,000 cubic meters. And the total air change per hour is 6 air changes per hour. Another definition, outside air. Outside air, by definition, is very specific here. It is external air, atmosphere exterior to refrigerated or conditioned space, ambient air, or we say surrounding air. Recirculated air is in fact the part of return air passed through the air conditioner before being resupplied to the conditioned space. We also know this as return air. Air conditioning is defined as the process of treating air so as to control simultaneously its temperature, humidity, purity, distribution, pressure, and air movement to meet the thermal requirements of the space. As you can see, this definition is very complete with respect to the criteria that goes into designing the air conditioning for a space. As indicated, the temperature must be analyzed, maintained accordingly for the end result of this space function. Humidity as well, air purity, the distribution, the pressure, and of course, air movement into and through the space is of importance. Now going back up to the first definition that we indicated, outside air. This is important because in our buildings that we cannot provide natural ventilation, we must provide mechanical ventilation. That is to take outside air into our air distribution system, air conditioning system, and mix it and deliver it to what we call the breathing zone to dilute contaminants within our buildings. And we'll speak more of that in a slide or several slides coming up. Air handling unit is defined as equipment comprised of cooling and or heating coil and a blower or fan with electric motor used for the purpose of cooling, heating, and distributing supply air to a room, space, or area. Below is a picture of an air handling unit. This air handling unit is equipped with chilled water and hot water supply and return. Ventilation. Ventilation is defined as the process of supplying and or removing air by natural or mechanical means to or from any space. Such air may or may not have been conditioned. Important definition here. However, positive ventilation is defined as the supply of outside air by means of a mechanical device such as a fan. The graphic that you see below is a description of a mechanical ventilation system. In the upper left-hand portion of the diagram, we can see the entry of the outside air. It is mixed with the return air at a certain volume and supplied into the supply air fan and then distributed into the occupied space. The air is returned through the bottom of the graphic into the return air fan. We have an exhaust, relief air, and return air moving back up and then mixing again with the outdoor air to provide good, clean, filtered air into the occupied space. And this is a good example of a mechanical ventilation system and air conditioning system. Section 2.5, General Provisions. This section provides references for air conditioning, heating, and ventilation systems, as well as associated electrical, plumbing, fuel gas, and fire safety requirements. Now, Section 2.5.1 references the ASHRAE handbooks, ASHRAE is the American Society of Heating, Refrigeration, and Air Conditioning Engineers. HI is referenced here, the Hydraulic Institute of USA. These manuals and relevant chapters of this code for air conditioning, heating, and ventilation systems regarding the following: design, construction, installation, operation, and maintenance, gives the code user a good design reference when it comes to designing air conditioning, heating, and ventilation systems by simply using these reference standards. This section provides references for air conditioning, heating, ventilation systems, as well as, again, the electrical, plumbing, fuel, gas, and fire safety requirements. When it comes to the electrical requirements, any electrical connections to air conditioning, heating, and ventilation systems must comply with Section 2.52. This section references the electrical provisions of the latest Bangladesh Electricity Act and the provisions of any of its regulations and bylaws, and must also comply with the requirements of Chapter 1. Section 2.5.3 gives us requirements for all plumbing work in connection with air conditioning, heating, and ventilation systems shall be carried out in accordance with the provisions and guidelines of ASHRAE handbooks and HI manuals. Additionally, Section 2.5.4 gives us requirements for all gas and fuel piping in connection with air conditioning, heating, and ventilation systems shall be carried out in accordance with the provisions of Chapter 8. Below is an example of a boiler that is a gas-fired boiler. As you can see, there is gas fuel piping, and in this case, the provisions of Chapter 8 would have to be followed. So this particular set of sections is giving us a direction for additional requirements to the air conditioning, heating, and ventilation systems that are very specific to plumbing work, gas, and fuel piping. The last section here, Section 2.5.5, deals with fire safety and indicates the following: installations of equipment of air conditioning, heating, and ventilation system shall conform to the requirements of Part 4 of this code. Again, given some direction to fire safety requirements of the equipment that is related to air conditioning, heating, and ventilation systems. Planning. Section 2.6 gives us the requirements regarding all relevant aspects of air conditioning, heating, and ventilation system installations. They need to be analyzed and evaluated properly during the planning stage of the building in order to determine the necessary provisions to be kept in the building for proper, safe installation of the system, machinery, equipment, and other facilities. There are many items in this section that will help the code user, the engineers, the architects in the designing of specific mechanical systems within the building. Section 2.6.1.3 helps us understand, where necessary, all plans, calculations, specifications, and data for air conditioning, heating, and ventilation systems serving all buildings and all occupancies within the scope of the code shall be supplied to the authority for review purposes. This is important, ladies and gentlemen, because the authority must review the necessary construction documents, the installation documents, the calculations, even the specifications and data for our mechanical systems that are very specific to air conditioning, heating, and ventilation. The authority makes sure that the systems have been engineered properly and can be installed within the buildings safely for their end use. Section 2.6.2.11, Design Drawings. For the purpose of effective installation of air conditioning, heating, and ventilation system, working drawings showing layout of machinery, equipment, ducts, pipes, etc., details of builder's works, holes and/or punches in roof, floors, walls, supports for machinery, equipment, etc., shall be prepared prior to finalization of building design drawings. Such drawings or documents shall be properly stored for future reference. Again, giving specific installation and layout drawings and routing drawings of the equipment and systems specifically is a requirement in this section. Ventilation air. Section 2.7 is titled Air Conditioning System Design Ventilation Air. There are two very important sections here that have to be noted by the code user. The first section is Section A, that indicates every space served by the air conditioning system shall be provided with outside fresh air not less than the minimum amount mentioned in Table 8.2.3. If adequate temperature regulation along with efficient filtration of air and absorption of odor and gas are provided, the amount of fresh air requirement may be reduced. However, in no case the outdoor air quantity shall be lower than 2.5 liters per second per person. When we read this section, there's a whole bunch of information in this section. What this section is talking about is what we call mechanical ventilation. And it gives a very specific table. Table 8.2.3 is referenced. We will take a look at Table 8.2.3 and give an example, work through a calculated example for ventilation, mechanical ventilation. As seen here, the minimum airflow quantity cannot be lower than 2.5 liter per second per person. We will find that there are a series of calculations that have to be made to determine how much outside air needs to be provided in a mechanical ventilation system. So we need this initial requirement as a basis for our design, installation, and final balancing of the system for verification. In hospital operation theaters, item B, a large quantity of outdoor air is supplied and recommended to overcome explosion hazard of anesthetics and to maintain sterile conditions. However, if adequate filtration with efficient absorption of anesthetics and laminar flow of supply air is provided, outside air requirement may be substantially reduced. Recirculation of air shall comply with the requirements of Section 2.11.3.6. This section is specific, as indicated, regarding hospital operation theaters. Granted, we have a huge amount of outdoor air that needs to be supplied to overcome the anesthetics and maintain sterile conditions. In other words, you will see when we enter Table 8.2.3 the amount of air that is required for hospital operation theaters. The very last sentence gives the directive of recirculation air that need to comply with section 2.11.3.6 if considered. Now, just to summarize, section 2.7.2.3a provides a requirement for outside of fresh air in reference to table 8.2.3, including a reduction of outdoor air where proper filtration and absorption of odor and gas are provided. So we could provide a reduction of outdoor air. Additionally, the outdoor air quantity, again, must never be lower than 2.5 liters per second. Last, section 2.7.2.3b provides very specific information and requirements regarding hospital operation theaters. Referencing Table 8.2.3 titled Minimum Ventilation Rates for Air-Conditioned Spaces, we will look into the minimum airflow rates according to these areas. Focusing on protecting the health of the building occupants, the provisions of this chapter provide requirements that are intended to control contaminants within buildings, such as carbon dioxide and contaminants from entering buildings, such as pollutants, vehicle exhaust from a nearby street, just to name a few. Ventilation in simple terms can be understood as introducing fresh air into a single-story office building by opening several exterior wall windows in order to dilute and possibly remove certain contaminants. That is what we call natural ventilation. However, the natural airflow through openable windows is not precisely controllable due to variables such as wind speed, wind direction, indoor and outdoor pressure differentials or differences, just to name a few. So again, where natural ventilation is allowed by this code, we will find out where it is not precisely controlled. Consider an office building without openable windows on the exterior walls. Providing ventilation air to occupied spaces within these types of buildings can be achieved by mechanically controlling air flowing from outdoor air louvers into the HVAC air distribution system that mixes with heated or cooled air and is distributed throughout ducts and diffusers and delivered to all occupied spaces within the building. When we take outside air into our air distribution system, we want to take that fresh air, we want to filter that fresh air and distribute it into what we call the breathing zone, which we will qualify coming up shortly. Table 8.2.3 is titled Minimum Ventilation Rates for Air-Conditioned Spaces. As seen here, the table gives us much information about the occupancy classification, airflow rates, and in the very last column, there's an exhaust airflow rate as well. This table 8.2.3, is based on ASHRAE 62.1 called the Ventilation Rate Procedure. This table prescribes both the use of 100% outdoor air as ventilation air and an occupant load calculation method for ventilation purposes only. The occupant load utilized for the design of the ventilation system must not be less than the number determined from the estimated maximum occupant load rate indicated in Table 8.2.3. Ventilation rates for occupancies not represented in Table 8.2.3 shall be those for a listed occupancy classification that is most similar in terms of occupant density, activities, and building construction, or shall be determined by an approved engineering analysis. Systematically describing Table 8.2.3 is as follows. We will look to the first column. The first column is titled Occupancy Classification. That resembles the function of the occupied spaces. As seen here, we have occupancy classification. Correctional facilities is a category with rooms indicated as such below the category. Dry cleaners, laundries, another category, given coin-operated dry cleaner, coin-operated laundries, commercial laundry, storage pickup. Education is another category. And as you can see, all of the areas within an education occupancy are given here with respect to the occupancy classification. Auditoriums, corridors, music, theater, dance areas or locations, classrooms, science laboratories, computer labs. We use the first column to fit the use or the function of the area within the building into what we call the occupancy classification. And again, that is the first column. The second column provides an outdoor air rate in liters per second per person. The outdoor airflow rate, we can say, has a variable that we'll title R sub P, the rate of airflow per person. We will use this to calculate the total outdoor airflow rate to be provided in the breathing zone based upon the total number of people in the occupied space. So simply looking into the second column of the table, as seen here, based upon the occupancy classification and the space within the occupancy, you are given a prescriptive outdoor airflow rate in the breathing zone in liters per second per person. Let's take an example. In an education occupancy classification for auditoriums, the minimum outdoor airflow rate in the breathing zone that we'll have to calculate is 2.5 liters per second per person. This is where we pick this variable, and we will integrate this variable into an equation and ultimately calculate the total outside air requirement for mechanical ventilation. This is just one part that we have to integrate into an equation that I will show you coming up in a slide later on. The third column provides an outdoor airflow rate in liters per second per square meter. We can say that it is the variable R sub A that will be used to calculate the total outdoor airflow rate to be provided in the breathing zone based upon the total area of the occupied space. Looking into the third column in the table, as seen here, the third column, outdoor airflow rate in the breathing zone. We'll do the example again, using the education occupancy classification, and again, the auditorium space. You can see that we have to provide 0.3 liters per second per square meter of space. Again, this variable goes into an equation to calculate the overall outdoor air to be brought in to the air distribution system in a mechanical ventilation system. The fourth column provides occupant density. Occupant density for ventilation only. So the fourth column will provide us an occupant density for the number of people per 100 meters squared of area that will allow the total number of people to be calculated for ventilation based upon the occupancy classification of the space. We will use the education, the auditorium space as the occupancy classification, and intersecting that with the third column, it gives us 150 occupants per 100 square meters. This is the value or the ratio that we will utilize in a calculation to calculate the population of the zone. We will go through this systematically and integrate what we have picked here in the table into an equation for the amount of people in this particular area. The fifth column provides an exhaust airflow rate in liters per second per square meter of occupied space that must be provided for certain occupancy classifications. The required exhaust airflow rate must be provided in addition to any other ventilation rates prescribed by the table. As seen here in the last column, not every space or room requires an exhaust airflow rate. Some spaces do. If we look at the occupancy classification of education again, we look to the sports locker rooms. And as you can see, the very last column indicates that there is an exhaust airflow rate for sports locker rooms at 2.5 liters per second per square meter. That has to be considered when designing and installing these ventilation systems for sports locker rooms. In addition, we have art classrooms in educational occupancies. And as seen here, the exhaust airflow rate now goes up to 3.5 liters per second per square meter of classroom that is specifically used for art. As an example, food and beverage service category, dining rooms must be provided with a person airflow rate of 3.75 liters per second after calculating the default occupancy density. The area airflow rate of 0.9 liters per second per meter squared must be multiplied by the area of zone. And the occupancy classification you can see here is food and beverage service. So what we're doing here is we are picking values from this table to integrate into an equation to ultimately calculate the total amount of outside air required for these particular spaces based upon the function of these spaces within our buildings. Another part of the table, continuation, indicates the occupancy classifications. Hospitals, operating rooms. We can see here the operating rooms have a very, very high outdoor airflow rate in the breathing zone at 15 liters per second per person. And again, we remember where that requirement comes from, and we see the high airflow rate in these operating theaters. Patient rooms give us 12.5 liters per second per person. And as you can see, based upon the function of the area, physical therapy, recovery, and ICU, both have 7.5 liter per second per person as a requirement, minimum requirement to provide that outdoor airflow rate in the breathing zone per person. Another category that must not be forgotten in our commercial buildings is public spaces. As you can see, some of the areas and locations in public spaces range from corridors to elevator cars, shower rooms, smoking lounges, toilet rooms, places of religious worship, courtrooms, etc. When we look into this a little closer into the public spaces category, for example, toilet rooms, public. After the word public, there is a note G. Note G refers the code user to the notes of the table. There's specific information about recirculation of that air regarding public toilet rooms. So we'll want to go take a look at note G of the table. Further, if you go to the very last column, the exhaust airflow rate column, there is another note after the values that you see in that particular column. Now, the toilet rooms have a note E after the 30 liter per second requirement. That E is an indicator that the rates are per water closet or urinal. So that higher rate is provided where we have heavy use, such as toilets in theaters, schools, sports facilities, things of that nature. The lower rate is permitted where periods of heavy use are not expected. Therefore, we have a simple way to provide exhaust requirements for our toilet rooms in public spaces. Continuing on with Table 8.2.3, we're going to another category, retail stores, sales floors, and showroom floors. As seen within this category, each area has its own requirements when it comes to ventilation and exhaust. The sales area, for example, needs to be provided with an outdoor airflow rate for people in 3.75 liters per second per person, as well as the area at 0.6 liters per second per square meter. Additionally, in order to calculate the people part of it, we need the default occupant density. And in this case, for sales floors, it's 15 people per 100 square meters. And we will work through a couple of calculations on a given example coming up shortly. The very last column for the sales, there is no exhaust airflow rate required. Now, when we move to specialty shops, that category, the first item, automotive motor fuel dispensing stations, there's note B. If you look to the bottom of the table, note B indicates that mechanical exhaust is required and the recirculation of the air from any of these spaces, like the motor fuel dispensing area, is prohibited. All air supplied to such spaces shall be exhausted, including any air in excess of that required by this code. That's note B, and as you can see, the exhaust airflow rate is given to us at 7.5 liters per second per square meter of area. This allows the designer to properly design the minimum exhaust airflow rate from these motor fuel dispensing stations. We need to remove the contaminants from these particular spaces. We also need to bring in 100% outside air for proper ventilation. So combining this exhaust airflow rate with the area automotive fuel dispensing stations in the specialty shop category, the engineer can design a safe system to remove any of those contaminants at this minimum rate. The inspector will go out and make sure that everything is constructed in accordance with the approved construction documents by the authority and continue the operation of that specific area. Another one is the beauty and nail salons. As you can see, there are four values in the table. The first value is 10 liters per second per person in the first column. There's our people airflow rate. The next column is 0.6 liters per second per square meter. That's our area flow rate. And we can calculate the people or the population in the zone by simply looking over the third column and running that ratio, if you will, in a calculation at 25 occupants per 100 square meters. Now further, this particular specialty shop also requires an exhaust airflow rate. And as seen in the very last column, it is 3 liters per second per square meter of floor area that is used as beauty and nail salon area. So as we look into these categories and the values in the table, we should be familiar with how to pick the values from the table and then utilize them in upcoming equations to calculate the total amount of outside air required for the zone. The notes to the table are given here. We have note A through H. Now, the notes are a function of the table. You need to reference the notes accordingly when they're referenced and when they're not. So the code user must always go to the very bottom of the table to, in fact, check to see if any of the notes are applicable to their design, to their inspection area. For example, note H. Note H is given to us for nail salons. This is a specific requirement here, and it gives you a specific exhaust requirement in the ventilation table for nail stations such as tables or other systems that need to provide a source capture system. Means a local exhaust system capable of exhausting 25 liters per second per nail station. That's a specific note. And as you can see, all of the other notes are pretty important with respect to different areas within our buildings. When we go to section 2.11.1.1 scope, the provisions of this section shall govern the ventilation of spaces within a building intended for human occupancy. Now, this is where we provide the requirements in the code for ventilation. Where required is given to us in section 2.11.1.2, in that every space intended for human occupancy shall be provided with ventilation by natural or mechanical means during the periods when the room or space is occupied. Now, this particular section comes out and gives the designer a choice whether to use natural or mechanical means. As we further discover the requirements in this particular section, we move to section 2.11.2.1, and this provides specific requirements regarding sources of natural ventilation. Where can we take natural ventilation from? Natural ventilation of an occupied space shall be through windows, doors, louvers, skylights, or other openings to the outdoors. We must take clean, fresh air into the building utilizing these openings in our buildings. Such ventilating openings shall open to the sky or a public street, space, alley, park, highway, yard, court, plaza, or other approved space which comply with the requirements of the building code. A word of caution here: when you have natural ventilation openings, we need to make sure that we do not draw in contaminants such as exhaust from the public streets, things of that nature. So it's up to the designer to properly indicate where these openings are going to be located on the building, again, to bring in clean, fresh outdoor air. The minimum ventilating opening to the outdoors shall be 4% of the floor area being ventilated. So there's a requirement now that once we calculate the floor area, we need a minimum of 4% openable to the outdoors. The contaminants that need to get exhausted cannot be overlooked here. That's why section 2.11.2.3 provides this requirement when we have naturally ventilated spaces. When we have these naturally ventilated spaces having contaminants present, these areas or spaces need to comply with the requirements of section 2.8.3. So it sends us in the direction of providing an exhaust system. After all, natural ventilation is essentially just bringing fresh air into the building. It does not provide a dynamic way to remove exhaust from locations such as kitchens, toilets, or bathrooms. And we need an independent mechanical exhaust system to provide the exhaust from those particular spaces to remove the contaminants safely. And we will go to section 2.11.2.3. As seen here in the graphic below, we have a bathroom exhaust system, and it is independent and serving that particular space only in a naturally ventilated building. And that's how we comply with this section, by understanding that we have a code section indicating contaminants that need to be exhausted, and the code is referring us to section 2.8.3 to carry out those requirements. So it's very important as inspectors, when you go out and look at the project periodically, to make sure that the independent exhaust system is installed accordingly and as designed by the engineer. Natural ventilation is given here. In order to provide natural ventilation, openings must communicate with the outdoor air. Openings to the outdoor air, such as doors, windows, or louvers, provide natural ventilation. In other words, we need openings to the exterior to draw in fresh air and properly ventilate the building. Not only draw in fresh air, but we hope that the air that's drawn into the building will somewhat disperse through the building and be exhausted out the same openings naturally. Again, there is no mechanical means to draw in outside air and exhaust stale air from the building. We are reliant upon pressure differentials within the building and the outdoor atmosphere. So the operating mechanism for such openings shall be provided with ready access so that the openings are readily controllable by the building occupants. In other words, we need to open up a window easily. We need to open doors easily. They need to be readily accessible. Now, in order to qualify for natural ventilation, the minimum openable area to the outdoors must have 4% of the floor area being ventilated. Note that section 2.11.2.2 A and B provide additional requirements where rooms and spaces without openings to the outdoors are ventilated through an adjoining room and openings below grade. So if your building is constructed where you have these particular openings where the outdoor ventilation must go through an adjoining room or maybe even openings below grade, you are directed to go to section 2.11.2.2 A and B, and there are additional requirements. In other words, the openings need to be bigger for those particular areas. But the general rule here is 4% of the floor area is needed to calculate the minimum openable area. Based upon the minimum required area calculated for openings, the locations of windows should be placed to allow air to flow through spaces. Windows only installed on one side of the building may not produce the function of natural ventilation. In other words, we need cross ventilation to take in air possibly from one side of the building where we have pressure differentials from that point of air entering through the building to the other side of the building and provide some means to allow air to flow completely through the building from one side and out of the other side due to the pressure differentials. Let's talk about an example of how to provide this natural ventilation. Consider a new one-story office building with floor dimensions indicated in the plan below. The proposed building is to be naturally ventilated. What is the required minimum openable area to the outdoors to be installed? As shown here, it's a smaller building, new office building. The dimensions, as indicated here, are 20 meter by 15 meter. The natural ventilation will be through openings such as windows, indicated as seen here on the exterior wall. These are openable windows. We need to calculate the building floor area to be ventilated. That's our first step. So simple calculation of area of the building is 15 meter by 20 meter gives us 300 square meters. We need to calculate the minimum openable area required by the section and indicating 4% of the area to be openable to the outdoors. So we come in and we calculate the minimum openable area. We take 300 square meters times the decimal equivalent of 4%, which is 0.04, and that equates to 12 square meters of minimum openable area that must be provided for natural ventilation. Now, when this method is provided, the authority must review the plans and make sure that the minimum openable area complies with the code. As inspectors out in the field or on the job site, we need to verify that the openings have been placed in their proper locations according to the approved construction documents, and verify that the opening area is compliant with the design and this code. Referencing mechanical ventilation, we go to section 2.11.3.4 for minimum outdoor air. The minimum outdoor air is required in accordance with table 8.2.3. That is the first part that's given to us in this section. And we recall from that table there are 5 columns in the table. The first column being the occupancy classification. The second column is the rate of airflow in liters per second per person in the breathing zone. The third column was the area airflow rate in square meters based upon the area of that particular occupancy or zone. The next column, the fourth column, was the occupant density column. We use the occupant density column to calculate the number of people in the breathing zone. And then finally, the very last column, as you recall, is the exhaust airflow rate that may or may not be required based on certain spaces in the building. Now, we're given that requirement here for minimum outdoor air. This is mechanical ventilation. That is the first part. The second part is a limitation, and the mandatory requirement calls out, in no case must the ventilation air quantity be lower than 2.5 liter per second per person. So there is a minimum airflow rate per person integrated here, and that should be reflected in the table in most cases. Mechanical ventilation. Ventilation systems shall be designed to have the capacity to supply the minimum outdoor airflow rate, determined in accordance with this section. In each occupiable space, the ventilation system shall be designed to deliver the required rate of outdoor airflow to the breathing zone. ASHRAE 62.1 defines ventilation air as that portion of supply air that is outdoor air plus any recirculated air that has been treated for the purpose of maintaining acceptable indoor air quality. The breathing zone, on the other hand, is the region within the occupied space between 75 millimeter and 1800 millimeter above the floor. The breathing zone, by definition, has specific defined boundaries based upon where people occupy spaces. As seen in the figure below, a general graphic representation indicating these boundaries of where spaces will be occupied. Notice the distance away from walls and air conditioning equipment. This is due to people are not generally located near walls, grills, and diffusers. The ventilation outdoor airflow rate, calculated based upon table 8.2.3, will be designed to minimize stagnant pockets and stratified layers of air and effectively installed into the breathing zone of occupied spaces. What's seen here in the graphic or figure below is the supply of air from the lower right-hand side being introduced into the breathing zone. This supply air is a mixture of conditioned air along with the required outdoor air for that particular zone that we call the breathing zone. It is then worked through or distributed through that breathing zone into the return air duct, and the continuation of supplying clean, fresh air into the breathing zone. So that is the overall basic function of mechanical ventilation in this particular application. Mechanical ventilation example. We will look at an example applying table 8.2.3 based on the ventilation rate procedure according to ASHRAE 62.1. At first glance, table 8.2.3 may appear to be unclear. However, we will reference ASHRAE 62.1, specifically section 6.2.2, in order to calculate the minimum outdoor airflow rate required to supply a single zone based upon the function of occupancy classification and space air distribution effectiveness as well. We'll work through an example of a single zone system in a step-by-step method to determine the outdoor airflow rate required in the breathing zone. We will call this V sub BZ. While applying zone air distribution effectiveness, we will call this E sub Z values, as well as calculating the zone outdoor airflow rate V sub OZ for the given application. Now, as you can see, the variables that we just discussed are going to be part of the equation. As an example, let's consider a new restaurant building is being constructed, and we need to find out by calculation and analysis how much outdoor air is required for mechanical ventilation of a dining room within a restaurant of this new building. Our example will focus on a single zone recirculating system. Two figures are indicated below, figure 1.1 and figure 1.2. Figure 1.2 on the right-hand side is a picture looking at a part of the dining room construction. As seen, we have supply ducts in the ceiling, and we will have a return air plenum. Figure 1.1 shows the ceiling with finished diffuser and return grill, both located on the ceiling. Below the ceiling in figure 1.1 gives the dimensions of this particular dining room area. 15 meter by 25 meters. We're going to determine the system's outdoor air intake flow rate, which is V sub OT for the dining room. Working our way through the example, we need to provide some requirements. In order to determine the system outdoor air intake flow rate, The breathing zone outdoor airflow rate, V sub BZ of the occupied space, must first be determined using ASHRAE 62.1, equation 6.2.2.1. Then, the zone airflow effectiveness, E sub Z, must be determined in accordance with table 6.2.2.2 and calculated with equation 6.2.2.3. Next, the outdoor airflow rate in the zone that's indicated as V sub OZ must be determined using equation 6.2.3. This is the process for calculating the minimum airflow rate that must be designed to be introduced into the air distribution and conveyed to the breathing zone for our example. The equation that's indicated below, equation 6.2.2.1, is as follows. We need to solve for the volume of outdoor air in the breathing zone, V sub BZ. That is equal to the rate of outdoor airflow per person, R sub P, multiplied by the population of the zone, P sub Z. We will calculate the population of the zone using the occupant density given to us from the table. We're going to take that quantity and add it to the quantity R sub A. This is the rate of outdoor airflow per area meters squared of our dining room. We will multiply that airflow rate times the total area of our dining room, indicated here as A sub Z. That is the area of the zone. As you can see, all the variables are defined accordingly. We will pick some values from table 8.2.3. We will pick the R sub P outdoor airflow rate for the people. We will pick the R sub A area outdoor airflow rate for the unit area accordingly. The next equation is given to us as V sub OZ. This is where we provide an effectiveness factor, one for cooling and one for heating. We will pick these values from a table, and this is going to be the airflow effectiveness coefficient, if you will, and this will derive a value to modify what we've calculated above, either modify it or keep it the same. In this condition where we apply an airflow effectiveness calculation, we must specify and design for the higher airflow rate. V sub OT is our last equation. This is where we will calculate the total amount of air required. And in this case, it's pretty simple. For a single zone system, V sub OT is equivalent to V sub OZ as we calculated in the equation above. Again, this is for a single zone system, equation 6.2.3. Keep in mind, there are other ways to calculate mechanical ventilation for multi-zone systems. ASHRAE 62.1 has other calculation methods for multi-zone systems as well. Our example will focus on only a single zone system. Step 1 of our example, we will determine the occupant density, P sub Z, for the dining room. Utilizing table 8.2.3 for dining rooms, the default occupant density is used at a ratio of 70 occupants per 100 square meters. Viewing the table below, as you can see, the category here of occupant classification is food and beverage service. The space that we will be utilizing for our calculation is dining rooms. And moving over to the fourth column, the value 70 is our default occupant density, 70 occupants per 100 square meters. So we will pick that first. Therefore, P sub Z equals 375 square meters times 70 divided by 100. This gives us 263 occupants. That is our PZ value, our population of the zone for ventilation. Step 2, we will determine the breathing zone outdoor airflow rate V sub BZ for the room. The outdoor air rates for people, R sub P, and the area outdoor air rates, R sub A, must first be obtained for the dining room from table 8.2.3. As indicated in the table below, the R sub P value, the outdoor airflow rate in the breathing zone in liters per second per person, is given to us at a rate of 3.75 liter per second per person. And the adjacent column, the outdoor airflow rate in the breathing zone for the area, is given to us as 0.90 liters per second per square meter. So we select those two values for our dining room in step 2. A continuation of step 2 now gives us our equation. Equation 6.2.2.1 can now be solved. We integrate these particular values in this equation, and as can be seen here, V sub BZ equals the quantity, 3.75 liters per second per person, times, remember our population of our zone, 263 people. We take the product of that portion of the equation and add it to the following portion of our equation, the area part portion, 0.90 liters per second per square meter, times the area of our dining room, 375 square meters. Therefore, V sub BZ equals 1,337 liters per second. Step 3. According to table 6.2.2.2 and applying equation 6.2.2.3, determine the outdoor airflow rate. What we will do is we will now take a look at the outdoor airflow rate, and we need to determine what is called the air distribution effectiveness. We noted that the supply air and the return air are at the ceiling level. This is important to apply this particular table, ladies and gentlemen. By applying this table in conjunction with the equation V sub OZ equals V sub BZ that we've already calculated, we simply divide what we call the E sub Z factor that's given to us from the table 6.2.2.1. Step 3 continued. It's given that the room is served by a rooftop air handling unit. Remember, this is a single zone system by means of ducted ceiling supply registers and ceiling return grills. Thus, the zone air distribution effectiveness, E sub Z, of course, can be obtained from table 6.2.2.2. In cooling mode, E sub Z equates or is selected as 1.0. Noting the table below, we do have ceiling supply of cool air. We will take that particular value and use it in the cooling portion of the equation. And in the heating mode, E sub Z is 0.8. This is given to us in the table. As indicated, ceiling supply of warm air, 15 degrees Fahrenheit or 8 degrees Celsius or more above space temperature and ceiling return. Again, a true statement for our air distribution arrangement accordingly. Below, we have two calculations to calculate the highest airflow rate. For cooling mode, we simply take our V sub BZ that we calculated prior, 1,337 liters per second, and divide it by the factor or the coefficient that we find in the table, EZ of 1 equals, again, 1,337 liters per second. However, in heating mode, we take the heating mode value, and as seen here in the denominator, it is less than 1, so that's going to drive up the end result to 1,672 liters per second. This is the value that we need to use for our outdoor airflow rate in this part of the process. Step 4. Section 6.2.3 states that where one air handler supplies a mixture of outdoor air and recirculated air to only one zone, the system outdoor air intake flow rate, V sub OT, shall be determined in accordance with equation 6.2.3 indicated below. Therefore, the total system outdoor air intake flow rate for the proposed restaurant dining room must be a minimum of 1,672 liters per second. As indicated in the graph, it will be designed and balanced such that we will provide this amount of outdoor airflow rate into the air distribution system, mixing it with return air, in this case, through the supply air fan and distributing it into the breathing zone accordingly. This is a good graphic of an example of how the air is returned back to the system on the lower part of the graph. Through the return air fan, we have exhaust relief as well as return going back up and mixing with the outdoor air and then resupplying it to the occupied zone. In this case would be our dining room. The last important feature that the designer and inspector must be aware of is that the outdoor air intake openings must be located to prevent contaminants from being drawn back into the building through the ventilation air inlet openings of the building. So the code user is directed to section 2.11.4.5 of this code for location of exhaust outlets, and also recommend the ASHRAE 62.1 table 5.5.1 titled Air Intake Minimum Separation Distance for information regarding the separation of the air intake and any source of contaminants. Figure 1.3 shows an outdoor air intake being ducted from the exterior wall louver through a motorized damper into the return air distribution duct. Adjacent to that, figure 4.1 indicates the outdoor intake location separation from the edge of the street regarding the closest possible point that vehicle exhaust is likely to be located. We must be concerned with respect to these contaminants and utilize both this code and ASHRAE 62.1 Table 5.5.1 as a resource to properly locate these outdoor air intake openings on our buildings to protect the people and occupants in the spaces within the building. This is the end of the presentation. Thank you for your participation.